Hi, welcome to Chapter 16, Acid-Base Equilibria, Overview Part 1, where we're going to talk about Arrhenius acids and bases, Bronsted-Lowry acids and bases, the autoionization energy, ionization of water, and the pH scale. So just a quick refresher, if you don't remember from your Chem 1 days, when foods taste sour, it's because they're acidic. So anything that tastes sour, if you read the ingredients, it's because it has an acid in it. Acid is a compound that produces what we call hydronium, which is H3O+, when dissolved in water. The word acid comes from the Latin word acidus, which means sour. Some general properties of acids: they conduct electricity, they taste sour, they react with metals to produce hydrogen gas, they change colors of indicators, and they react with a base to form salt and water. Bases, or antacids, are kind of like when you have heartburn, you take an antacid because you're taking a base to kind of neutralize the acid in your stomach. A base is a compound that produces hydroxide or OH- ions when dissolved in water. Unlike acids, not all bases react with metals. Actually, most don't react with metals. Some general properties of bases: they conduct electricity, they're electrolytes. They taste bitter. They feel slippery. They can change color of indicators, and they will react with an acid to produce salt and water. So there's a couple definitions of acids, and the first one we're going to talk about is the Arrhenius acids and base. This was the first theory or definition of acids and bases. And basically what Arrhenius said is an acid is a substance that when dissolved in water will increase the concentration of hydrogen ions. Okay, so since it's dissolved in water, when you have a hydrogen ion in water, it can produce hydronium. So we will use H plus or hydronium interchangeably. Okay? An Arrhenius base is a substance that when dissolved in water will increase the concentration of hydroxide ions. Okay, if a base is an ionic hydroxide, it will dissociate to form the OH ions. If a base is reacting with water, it will remove one of the hydrogens from the water, leaving OH in the solution. So let's revise our definition a little bit, because Arrhenius' definition requires a substance to be aqueous. It has to be in water. Aqueous means in water. Can't we have an acid or a base that is in some other solvent? Yes, of course we can. But we have to broaden our definition. We can't really call it an Arrhenius acid or base. So two scientists called, one by the name of Bronsted and the other one Lowry, came up with a broader definition. And in the Bronsted-Lowry definition, an acid is a proton donor. And a proton happens to be H+. Think about it. If you remove the electron from hydrogen, you just have a proton. And a base is a proton acceptor. So let's look at this example here. Remember, Bronsted-Lowry acid is a molecular ion that is a proton donor. So let's look at our equation here. Here we have HCl that will become Cl-. So what happened to it? It had to lose a hydrogen or donate it. So if you're donating the hydrogen, then this would be your Bronsted-Lowry acid. And if you're accepting the hydrogen or the proton, this would be your Bronsted-Lowry base. Remember, the base accepts and the acid donates a proton. Sometimes a compound can be both. It just depends on if it's donating or accepting the proton. So in this example here, we have water plus NH3. In order for water to become OH-, it had to donate a proton. So in this case, it's the Bronsted-Lowry acid, and this would be the Bronsted-Lowry base. What if I now have water reacting with HCl? The water has to become H3O+, so it had to accept. So now it's a Bronsted-Lowry base, and this is a Bronsted-Lowry acid. When you have a substance that can be either an acid or a base, it's called amphoteric. And it really depends on what it's reacting with. If water is reacting with an acid, it will be the base. If water is reacting with a base, it will be the acid. The third acid-base theory or definition, and the most broad, is the Lewis acid's base. So up to this point, we had Arrhenius, which said it had to be in water, and you either produce H plus if you're an acid or OH minus if you're a base. Then Bronsted-Lowry came along and said, why does it always have to be in water? So they made it more general, and they just said the acid donates a proton and the base accepts a proton. But Lewis came along and said, can't we have an acid that doesn't contain hydrogen? And according to his definition, yes, we can. His is the most broad. And basically what Lewis said, and this is the same guy who did the Lewis diagrams, a Lewis acid is an atom, ion, or molecule that accepts an electron pair. So in Bronsted-Lowry, it was donating a proton. Now you're accepting an electron pair. And then Lewis base donates the electron pair. So what on earth does that mean? So let's look at our reaction here that we have. So in order for this fluorine to bond to BF3 and make BF4, we have no electrons here for the bonds to occur, so the fluorine has to donate the electron pair. So if it's donating the electron pair, this is a Lewis base. And if you're accepting, then you're a Lewis acid. And just a little rule of thumb, the more negative substance would be the base. So let's summarize our acid-base definition. So we have Arrhenius, which says that it has to be dissolved in water and you'll produce hydronium or H+. And your base will produce hydroxide. Then Bronsted-Lowry says, why does it always have to be in water? So it does not have to be aqueous. And you're donating a proton or accepting a proton. You must have at least one removable proton to donate in order to be an acid. And you must have at least one non-bonding pair of electrons so you could accept the hydrogen or the proton. And Lewis acid says you're an electron pair acceptor, an electron pair donor if you're a base. So water as a proton acceptor. So when hydrogen ion is formed in water, it does not exist alone for long. The hydrogen bonds with water. So here you have your H+, and it will bond with water to make hydronium. Okay? Again, Bronsted-Lowry acid must have at least one removable proton to be an acid, so you have to be able to donate it. And the base must have at least one non-bonding pair of electrons to accept the proton. So here we have our hydrogen that can be donated. And here we have our electron lone pairs here, non-bonding, that can accept it. So that's why this is a Bronsted-Lowry acid and a Bronsted-Lowry base. What is different about water? Water can act as a base and accept a proton and form an acid on the previous slide. So it could act as a base or an acid. So it can donate a proton and act as an acid, or it can accept a proton and act as a base. This makes water amphoteric. If it can be either, if it can be an acid or a base, it's amphoteric. So here are three other examples of substances that can be an acid or base. What causes something that is amphoteric to be a base or an acid? It depends on what it's reacting with. If these substances are reacting with acids, then they will act as the base. If they're reacting with bases, then they will act as the acids. What happens when an acid dissolves in water? Water acts as the Bronsted-Lowry base, and it'll it'll take the proton from the acid. So here, this is acting as the Bronsted-Lowry base, and this is acting as the Bronsted-Lowry acid. And this proton will move from here to here. It'll take it. Remember, you have your lone pair sitting here. As a result, the conjugate base of the acid and a hydronium ion are formed. So I mentioned something on the previous slide, a conjugate base. What are conjugates? So two formulas that differ by an H plus are called conjugate acid-base pairs. Reactions between acids and bases always yield their conjugate acids. So let's take this example here. We have HNO2 reacting with water, becoming NO2 minus plus H3O plus. First of all, what is happening here? So this substance is donating a proton, so that is why it's the Bronsted-Lowry acid. Once it donates that proton, what does it become? It becomes NO2 minus, right? So this is my acid, and its conjugate base is NO2 minus. So if you had to come up with a definition of a conjugate base, conjugate bases have one less H plus than the acid. So now this is my base, right? And if I want the conjugate acid, so now H2O is my Bronsted-Lowry base, and the substance that pairs up with it is H3O plus, and this is my conjugate acid. So my conjugate acid has one more H plus than the base that it's paired up with. So let's do some practice here. What is the conjugate base of each of the following acids? So remember, when you're writing the conjugate base, you're going to remove an H plus. So if I remove an H plus, it becomes more negative. If I remove an H plus, it becomes more negative. And you're subtracting 1 because you're only removing one H plus. This becomes a negative 2 because it was a negative to begin with. What is the conjugate acid for each of the following bases? So now I need to add an H plus. So I'm going to become more positive. So this had a minus 2, now it has a minus 1. Now that's positive, and that is neutral. Okay, so HSO3 minus is amphoteric. How do I get rid of this? Okay. Write an equation for the reaction with HSO3 minus with water, in which the ion acts as an acid. So we have HSO3 minus plus water and the ion is acting as an acid. And what is the definition of an acid? An acid is a substance that is a proton donor, so it's going to donate the H plus. So that's going to make now write an equation for HSO3 plus water, in which the ion acts as a base. So now this is acting as a base. So it is accepting the proton So not all acids and bases have the same strength. And here we have a list of the strengths of acids. So here you see everything above here is what's considered a strong acid. Everything from here down is basically not acidic at all, very small acidic. Everything from here down is a strong base. Everything from here up is kind of like weakly basic, if any at all. And then in the middle we have a range. So notice the acid strength, as I go up, I become stronger. And the base is as I go down, I become stronger. Strong acids completely dissociate in water, so their conjugate bases are quite weak. So HCl will break apart into H plus and Cl minus. So HCl is a strong acid. Cl minus, which is its conjugate base, is barely basic. It is super duper weak. Very, 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 very weak. The stronger your acid, the weaker your conjugate base. So weak acids only partially dissociate, so their conjugate bases are stronger bases. Okay? And substances that have very little acidity do not dissociate in water, so their conjugate bases are extremely strong. So acid's base strength. In every acid and base reaction, equilibrium, remember this from last chapter, favors the transfer of a proton from the strong acid to the strong base, and then forming a weak acid and a weaker base. Another way to say this is, in an acid-base reaction, the equilibrium will favor the reaction that moves the proton to the stronger base. So here we have a reaction. HCl plus water yields hydronium plus Cl minus. Water is a much stronger base than Cl minus. Remember I said Cl minus is very, 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 very weak. So water is stronger than that. So the equilibrium will lie far to the right. So remember, you want to, again, in an acid-base reaction, the equilibrium will favor the reaction that moves the proton to the stronger base. So this is going to be more favorable. So the forward reaction is more favorable here, which means you're going to produce more products, which means your equilibrium K is going to be greater than 1. Let's take this example here. In an acid-base reaction, remember, the equilibrium will favor the reaction that moves the proton to the stronger base. So in this reaction here, which is the same as up here, this is just written differently, but they're both acetic acid plus water yields hydronium plus acetate. Acetate, let's find acetate on here. And let's find water. Those are our two bases. Which one is stronger? Acetate is lower, so it is stronger. So acetate is the stronger base. So that's the one where you want the proton to move, right? So you need your proton to go here, which means this reaction has to move in the reverse. So it's always going to move towards the weaker side, right? So if it moves to the reverse, then your equilibrium constant K here is going to be less than 1 because you're going to end up with more reactants than products. So let's try this one here. And I just wrote this, I copied it from the last slide again, just to kind of reiterate it. In an acid-base reaction, the equilibrium will favor the direction that moves the protons to the stronger base. So here, for the following proton transfer reaction, predict whether your equilibrium K is greater than or less than 1. So let's look at what we have here. We have so this is my Bronsted-Lowry acid, and this is my Bronsted-Lowry base. And this is the acid, and this is the base. Okay? So let's compare our bases. So here we have CO3, 2 minus, and HCO3. This CO3, 2 minus, is stronger than HCO3 because it is lower here. So if I'm comparing these two, this one is stronger base. Oh, I'm sorry, I'm comparing the wrong ones. SO4 2 minus. And this is the stronger base. This is the weaker base. So which way is this going to move? So let's go back and reread it. In an acid-base reaction, the equilibrium will forward the reaction that moves the proton to the stronger base. Here's my stronger base. So this forward reaction is going to occur. So since the forward reaction is going to occur, I'm going to make more products. My equilibrium will be greater than 1. So again, water is amphoteric. So in pure water, a few molecules will act as a base and some will act as acids. This is referred to as autoionization. What is your equilibrium constant for this reaction here? So let's remember what we did in chapter 15. So Kc, remember, solids and liquids are not in your equilibrium constant. So it'll be equal to your products only. So this will be your equilibrium constant for the self-ionization of water. And that's what's written here. And because this is for water, they change it and they call it Kw. And they give it a name. Ion product constant for water is Kw. Okay. At 25 degrees C, Kw equals 1 times 10 to the negative 14. And that number 14 should ring a bell, the pH scale, right? So if your solution is neutral, then your concentration of H plus and OH minus are equal to each other. And that would be, they would each be 10 to the minus 7. If your solution is acidic, your concentration of H plus has to be greater than your concentration of OH minus. And if it's basic, then your H plus will be lower than your OH minus. Again, this Kw is just like Kc that we calculated in chapter 15. We just put the W here because it's for water. And it will always be hydronium times hydroxide. And if it's at 25 degrees C, it'll always be equal to 1 times 10 to the minus 14. So in pure water, again, the concentrations are equal to each other, and they will each have this molarity. If we wanted to calculate the pH, you just take the negative log of the concentration of your hydronium. Why the negative log? Well, if I took the log of this, I'd get a negative 7, and then you take the negative to make it a positive number. So therefore, in pure water, the pH is 7, and we know that is called neutral, right? If an acid has a higher hydronium concentration, then the pH is going to be less than 7. Don't get confused. Which number is larger? This one, okay? So that, if you take the negative log of that, you will get 5, which gives you an acid, right? Actually, I should make this 9 until they add up to 14. A base has a lower concentration, so the pH is greater than 7. And here's the pH scale of some common substances, okay? But I wanted to draw your attention to down here. How do you know how many significant figures or decimal places to write when you take the negative log of something? Well, when you're taking the negative log of a number, you count the amount of significant digits of the substance you're taking the negative log of. And that's how many decimal places your answer should have. So if this has 2 sig figs, then you need 2 decimal places. There are other P scales, okay? P just means the negative log. So you could have POH, so that's just a negative log of hydroxide. You could have PKW, and that would be just the negative log of KW. So P means the negative log. Again, if you do hydronium times hydroxide, you're going to get Kw, which is equal to 10 to the minus 14. If you take the negative log of everything here, you're going to get that the pH plus the pOH equals 14, or pKw. Okay? If I give you this concentration for hydronium, you can calculate the concentration of hydroxide if it's at 25 degrees C. The two of them multiply times each other equals 10 to the minus 14. So you just plug 10 to the minus 4 times OH minus equals 10 to the minus 14. So you're dividing, and you get that the hydroxide is equal to 10 to the minus 10. How do we measure pH? So there's a couple ways that you've probably done in the past. pH paper, if you own a pool, the little strips of paper you dip in the water to see, or a fish tank, you see what color it changes. You match it up with some pH range. You know, if it's a certain color, it tells you the pH. One of the better ways to measure it is with a pH meter. And that just uses, remember I said at the beginning, your acids and bases are electrolytes and they conduct electricity. So it kind of uses the voltage that gets generated and it converts that to a pH. But you could also use indicators. So here's a bunch of different indicators and the pH range that they work at. And then there's something called a universal indicator. And what they do is they mix these indicators together so you can get the full range. And that's what your pH paper is. It's kind of all of them kind of mixed together. And that is the end of part 1.